Alright, so welcome to today's YouTube video, and in this video we are going to be solving a very fun and highly educational LeetCode problem. The plan is for every single LeetCode weekly challenge, we are going to be solving and selecting one problem that will offer the maximum educational video content. So the idea is after a series of such videos, we'll be having a playlist where we are only solving hand-picked selected problems which offer the maximum educational content, right? So let's dive in to today's problem that we have selected from weekly contest 438, and today we have picked up the last problem or the hardest problem in the entire problem set. It offers a lot of learnings in terms of learning about how do you transform and how do you reduce the problems into simpler subproblems, and of course how to apply standard algorithms such as binary search in order to solve this problem. So let us look at the problem statement that is given to us. We are given n points on perimeter of a square, and we are required to select some k points out of the given n points such that we want to such that the minimum Manhattan distance between any 2 points that we have selected should be as large as possible, right? So we want to maximize the smallest distance between the k selected points that we have chosen. For example, let us take a look at this sample input. So we are given this square, and on the perimeter of square we are given 5 points A, B, C, D and E, right? And we are given k equals to 4, meaning that we have to select exactly k points out of the given 5 points. So the sample output for this particular sample input should be 1, and that is going to be if we decide to select B, C, D and E. Why? Because the smallest distance between any two of these 4 selected points is going to be B to C or C to D, which distance is going to be exactly be 1 unit of length, right? Instead, if we were allowed to select exactly 3 points, if k was equals to 3, then the answer could have been actually 2. How? We would have ended up selecting points B, D and E, and now you can see each of the pair of the points are the distance is going to be greater than equal to 2. So for k equal to 3, for this set of given 5 problems, for set of 5 points, the answer would have been 2, but for k equals to 4, for this sample input, the answer is exactly 1. So as I was trying to solve this problem, as I was going through this problem, the very first trigger point for me was that I want to maximize the minimum distance from any pair of 2 points that I select, the k points that I've selected, right? So the trigger point for me was that this follows a pattern of maximizing the minimum. So this is standard pattern of binary search, which is called as minimax, where you minimize the maximum or you maximize the minimum possible of some particular element. So this hints us very directly, the problem literally screams that, hey, probably you can solve this problem using binary search. So we'll just keep that observation on the back of our mind, and probably we are first going to try to think about, because it is not trivial to think about in two-dimensional coordinate kind of setting, how actually can you apply binary search, right? That is not trivial, that is not straightforward, but we have some idea that probably this still looks like a binary search problem. So we'll just keep that observation at the back of the head, and then we'll try to simplify this particular problem. The basic idea is, even though this looks like a two-dimensional problem and we need to compute Manhattan distance between 2 points which are two-dimensional points, the key idea is all the points that are given to us lie on the perimeter of the square. So this looks like there is some form of linear intuition on top of this square, even though points are given to us in two-dimensional. And with this, we set out to simplify the problem. This hints us that, hey, let us try to transform this two-dimensional problem into, let's say, a single dimensional problem. So that should be the starting point that gives us the hint for the next step. So the very first set of transformation that we can think about is this step itself. The first observation is Of course, let's try to start from two-dimensional geometry. If I'm trying to find out the Manhattan distance between any 2 points, let us say point C and point E, what is the Manhattan distance? If you recall, if you can retrace any path from any shortest path from the like point C to E, that is going to, like, number of steps that is required by you, number of steps that you're taking in north, south, east or west direction, right, is going to be the Manhattan distance. For example, from C to E, the distance is going to be, take a right, this is 1 unit length, take a north direction, 1 unit in the north, and then take another on the east direction. So this requires a traversal of 3 unit steps. So the Manhattan distance between to C to E is going to be 3, right? The basic observation is we can transform every such single shortest path such that we come up with a path which all the steps actually lie in the outer perimeter of the square itself. How? I can transform this sequence of step by this blue path into a path that only follows in the perimeter of the square. How? Instead of taking right and then up and then right, I can take right and then up. So this blue path can be transformed to this step 1. This is going to be the step 2, again a right, and then finally the third step, which is going to be up. So you can see there can be multiple shortest path between C to E. Our observation is it is always possible to select a path on the perimeter of the square itself. This is going to be useful very soon because we are going to be transforming this two-dimensional grid into slightly simpler version of the problem, right? So the idea is now we know that in a given square, we can actually select the smaller arc or on the perimeter of the square itself, and that is going to be giving us the Manhattan distance, right? And this simplifies. In the two-dimensional grid, we were requiring to compute the Manhattan distance, but now you can imagine a circle with perimeter as 4 times the side of the original square. Now you imagine that constructing a circle like this, and now you can very nicely plot the points A, B, C, D, E on top of this circle. The idea is if the distance between A to B is 1 unit length, the idea is the length of arc of this perimeter from A to B is also going to be exactly 1 unit length, right? So we have transformed the square into a circle, and now it is much simpler to talk about the distances, and we can think about it very nicely and very intuitively on top of this circle. So the problem reduces now that you are given a circle and you are plotted some points on top of it, and now you want to select some k points such that the minimum distance between any pair of 2 points that you select should be as large as possible. Now it is easier to imagine in terms of very familiar Euclidean distance and on top of this circle. So now we can start trying to build up a binary search solution on top of this particular circle. How can we do that? We can try to, coming up from the original observation that we had put in the back of our mind, we can actually do a binary search on selecting that minimum distance, or binary search on the answer itself, which is going to be the minimum distance between any 2 pair of points that we are going to end up selecting. Once we do a binary search on that, what is going to be reduced is we'll try to find out how many number of points actually we can start doing, that we can start selecting, which honors this condition of for a particular fixed value of d. So I'll give you an example, and that will make things super clear. So for example, let us say at some point of binary search, our distance d is going to be, let's say it is going to be 2. Okay. So the idea is, the sub problem that is that we are able to reduce is, can we find what is the maximum number of points that I can select such that the distance between any 2 selected point is going to be greater than equal to 2. So that is the sub problem. Let us try to solve it with a dry run. I don't know whether a point should be selected in the optimal set or not. So my first idea is, okay, let me select a point, and then now the next point that I'm going to be selecting should be with a arc length greater than equal to 2 distance. So the distance between these A to B is going to be 1. So unfortunately, if I've selected A, I cannot select B. So that is the key idea, that I've selected A. Now the first point, which is greater than equal to 2 distance, that is the next point that I am allowed to select, right? So the next point that I can select is going to be C, right? And once I've selected C, I'm again going to do, and I'm going to again try to pick the next possible point. I cannot pick the point D because C to D, the arc length is again going to be of distance 1. I want to pick the next point greater than equal to distance equal to 2, right? So the next point that I can select is going to be E. And once I've selected point E, I have maximized the number of points I could have selected such that the distance, minimum distance between any 2 points is greater than equal to D, where our D is currently equal to 2. So as you can see, if this is the condition that I want to pick up a subset, जिसमें कि every 2 points the distance is going to be at least 2, then I can at max choose 3 number of points. So this is the answer is not going to be D equal to 2. Why? Because we wanted to pick out in the original problem, we were given that you have to select 4 such points. So this tells us I cannot select 4 points while honoring the condition that the shortest distance that is going to be between any 2 points is going to be greater than equal to 2. So I cannot come up with such a selection. This is what I'm able to solve by using the greedy approach. We know the answer for this is going to be 1. So let us try to imagine that, okay, D instead of 2, let us say D is actually equal to 1. Okay, so in that case, let us say that I started with the first point that I'm selecting is A, right? And again, keep in mind, it is not necessary that A is going to be selected. But again, let's say A is what we are selecting. Then we can select B for sure, because A to B arc length is going to be 1 unit. Then I can of course select D also. Then I can of course select D. And then of course I can also select point E as well. So as you can see, if distance, the minimum distance that we are enforcing should be greater than equal to 1, then we can end up selecting all the points, 5 points. So we can select more than K points. So that means for D equals to 1, definitely answer is possible. To make such a selection is possible. So again, maybe we'll try to try to find it for D equals to 1.5 next time. And again, we are going to check out that, okay, if I'm going to be selecting A, then if A is the first selected point, then I cannot select B because the distance is going to be 1. The next earliest point that I can select is going to be C. Again, I cannot select D because arc length is 1. Again, the next point is going to be E. So again, in this fashion, we know we cannot make such a selection. And again, we also do not know if A should be in the optimal set. So again, what we are going to do in the next iteration, we are going to be figuring out, what if I do not select A and if I start by selecting B, right? And then I'm going to again continue doing that. Again, I'll be ending up selecting D, and then I cannot select A or E either, right? Or maybe, yes, I can actually select E because the distance arc length is going to be greater than 1.5, right? So again, this is the optimal. Again, this is less than number of points that we were required to select, which is 4. So again, this 1.5 is also not giving us the correct answer, as you can see. So the basic idea is there will be a range of D. If I'm going to be plotting, right, if I have to imagine it something like this, the distance D, if I'm going to be imagining, we know that for a particular small set, the answer is going to be yes for a limited value of D, and beyond a point of D, the answer is going to be end up no, right? On the y-axis, this is the Boolean axis where we are finding out yes or no answer to the question, is it possible to select greater than equal to K number of points? So this looks like a perfect candidate for binary search. So we can actually find out the minimum distance. This is what binary search is going to give us to, right? It is going to find us that boundary condition between yes and no, and this would be the smallest distance such that it is possible to select greater than or equal to k number of points. So this is the basic idea, and this greedy part of whether, like, for a particular fixed d distance, is it possible to find, like, k or more points that we can select. This greedy part, if we implement it naively, that is going to take us O of n square time. Why? Because we started with first selection as a, and then it required us traversal of n other points, and then we are able to find out, if I select a as my first point, then what is the maximum possible number of points I can select such that distance between any two is greater than equal to d, right? Similarly, we'll have to also consider the case where we are not selecting point A, and instead we are starting our first selection of point as B. And again, you'll have to go through all the n points, and then again you have to do it for the third point, fourth point as the first starting point. So there are n cases, and each of these n cases is actually requiring us traversal of another n operations, right? So this is overall O of n square. If you actually implement it in the naive fashion, this is going to be n square, and this is not going to fit with our requirement of the given constant, right? So what we can do, we can actually optimize this greedy of, for a given particular fixed distance d, can we select k or more number of points such that any 2 points have greater than d distance. So this part we can again use binary search subsequently in a nested format, so that we can also solve this sub problem by using a binary search algorithm. How can we do that? The idea is, okay, if I am having a, if I can maintain the entire all the points as a linear array, if instead of imagining it as a circle, if I can imagine it as a linear array, then I can simply do binary search with lower bound, and I'm going to find out the next point at distance a plus d from the origin. If this is the origin point, then I'm going to be finding if it is possible to find the next point after arc length distance of d. So if I do a binary search, I can find the next possible point that I can select in just log of n times, right? So in log of n times, you can find the next possible point that you can select, and again from C you can do another binary search, and you can find out that, okay, the next possible point is directly going to be E. So instead of O of n square, you can actually this is taking us logarithmic time for every subsequent selection, right? So there can be k possible choices. So we are actually doing k times this binary search. So this is k of log n if we have fixated a as our first selection of our point, right? And again, as we already know, there can be multiple possible selections of the first point. We don't know if selecting A is optimal, so we'll also want to start our search by selecting B as our first point. And then again, this is going to repeat. The next point will be found out in n, and then the next point is going to be found out in n. We want to select at least k, so this is again going to take k of log n, right? So our choice of first point is going to be n different choices, and for each of these choices we are going to be requiring k of log n time. So instead of n square, we can do n into k into log n, and this is better because the maximum possible value of k as per the constraint is only 25. So this is a much more efficient solution to actually solve this problem. And now this gives us the final solution, and this is the basic key intuition. All the key intuition required to solve this problem is already covered. The rest of the part is how do you efficiently transform it into a very simplistic kind of code, because implementing this in a code is going to be difficult because this is circular in nature. So I also have to find out the distance from here to here, or I can also find the distance from here to here. There is a circular nature. So how do you implement it efficiently? That is the only remaining piece of the puzzle. But we know that we have solved this problem very, very efficiently, right? So we already have solved this problem, but how do you implement it very nicely and very cleanly? So in order to do that, we have the last trick in our book, which is going to be very standard kind of trick that I'm not going to be covering in detail. The basic idea is whenever you're given a problem related to a circular function, that you can select anything from anywhere to anywhere that is a circular kind of function. You can reduce it into linear by imagine this circle and let's cut it from imagine this to be a circular thread and cut it from point A, which is our origin kind of, so and then elongate it and convert it into a length of array, correct? So if you can imagine this length of array, and the length of this array is going to be of this linear thread is going to be 4 times the side of square. Now double that array and add additional copy of this. So now if you do this, doubling the array, this is called as doubling the array trick. If you do this, now you can actually figure out every single circular transformation in this linear array. So this is the next transformation that we can reduce. This is a very standard trick. I'm not going to go into detail. The basic idea is instead of handling the circular nature, we can simply reduce it into a linear array and double the array, right? And now we can find out all sorts of circular kind of distance. As you can see, distance from A to E, the larger arc is represented by golden path, whereas the smaller arc, which is represented by the blue arc, in this particular diagram, once I've doubled this entirely, and this length of entire linearized array is going to be 8 times side of the square. So how can I find this corresponding golden, the larger arc here? How can I trace it out? This golden arc is going to go from A to E itself, right? This is the larger arc. How can I trace corresponding smaller arc in this linearized array? Here E to A dash is representing the corresponding smaller arc, right? So if we would have not doubled the array, then we would have lost out, or we would have missed out on the smaller arc from E to A, right? So we did not want to miss it, and that is exactly why we have doubled this array, right? So this is a standard trick. I'll probably link you some problems, a lot of problems which requires palindrome kind of situations. This kind of trick, where you are trying to find out palindrome on a circular kind of array, or you're trying to find out maximum sum subarray on a circular array itself, right? So in all of those kinds of problems, this doubling of the this doubling trick is very well utilized to convert a circular function into a truly linear function. And now applying the same algorithm that we did on a circle, if we can apply it on the linearized array, that is going to be make our lives and our implementation is going to be much easier. So this last part, the last trick that we did, transforming it into a true array itself, is just a trick to make our implementation a lot easier, right? But the entire solution, you can solve it just by imagining the circle itself. So this last trick is just a good implementation trick, and using this, we can actually solve the problem very, very efficiently using the binary search, the last binary search that we actually discussed, right? So this is what we are able to do. This we have already discussed. The third part we have already discussed. And again, we have already discussed how to compute predicate very, very efficiently, right? So this is the entire solution, and we have already gone through the entire solution. Final part of this problem is to analyze the time complexity. We had already analyzed that for a fixed particular D, if we want to find out is there existing possible selection of k or more points such that the minimum distance between any 2 points is greater than equal to a fixated D, we had already seen that time complexity was n into k into log n if we efficiently used binary search in order to continue finding the next potential point that we can select if we have selected a particular certain point, right? So that was n into k into log n. The final log of side is the parent binary search, the original binary search, where we are actually applying binary search on the possible values of D itself. So that is going to be the maximum possible size is going to be the size of the side itself. So that is why we are having a log of side. In actual final solution, it should be 8 into side, but again, it is big O notation, so we do not care about exact number of operation. and this gives us the final solution time complexity, and this is super efficient, and this is very easily going to pass in the given constraint. So this was the hardest problem of the today's contest. In my opinion, it is not so hard once you're able to apply these transformation. But what I really loved about this problem is it required us a step of sequences, right? We were able to figure out that maybe, that we can use binary search in order to solve this particular problem. But how do you apply binary search on a two-dimensional grid, two-dimensional point? So we required a set of deductions or transformation where we transformed the two-dimensional grid into a circular format, and then we broke the circular into a truly linearized array, and then we were able to apply binary search on this. So the cool part about this problem is this set of steps of transformation, and then the binary search part is like fairly straightforward, and we are using nested binary search to come up with the final super efficient solution to this particular problem. So this is all for today's this LeetCode contest's hardest problem. So the next LeetCode contest we are going to be seeing, and again I'm going to be picking up the most interesting and the most educational problem. So with this, I'm going to be ending this video. I hope you enjoyed this video. Feel free to leave any comments or any doubts that you may have with this problem. So that's all for today. See you, and keep you posted. You can sign up and subscribe to the channel. I'm planning to continue posting videos like this for the next LeetCode and the next LeetCode for the next 10 or 20 LeetCode contest live right after every single contest end. So that's all for today, and I hope you actually enjoyed learning all the educational content and educational value that you can learn and squeeze out from this particular problem statement.